Alright, today we're going to start chapter 7. We're only going to do the first section for this chapter. We're going to talk about gravitation. So section 1 is planetary motion and gravitation. What we're going to talk about today has to do with how the different planets move within our solar system, how they orbit, how they use their ellipticals, and how gravity is going to play into that. So first thing you need to know is what a gravitational force is. And that's any force of attraction between two objects. And it has to do with their mass, first of all. And it also has to depend on how much space is between them. So force is dependent upon their mass. So law of universal gravitation, this is Newton's law. He states that objects attract other objects with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay, and I know that's a little bit confusing, but basically what this is saying is that any two bodies or any two objects, anything that has mass, the closer they are, the more force they're going to have. So the more gravitational force they're going to have. So let's say, for instance, in class today, Gracie may be sitting close to Austin, so they have a greater gravitational force than Gracie would have with, let's say, Kyle, who's several desks away. So there is a certain way to find gravitational force, and it's based specifically on the law of gravitation. So we said that it's directly proportional to mass, so that's going to be in our numerator, and it's inversely proportional to the distance squared. So we have force, that's your gravitational force, equals big G, and we'll talk about that in a minute, multiplied by your mass of the first object, mass of the second object, and then divide by your distance squared, or the radius squared. So the distance from the center of one object to the center of another object, that's your distance, that's your radius that we're looking at here. So force, gravitational force, it's always going to be in newtons, that's what force is. G is a universal gravitational constant. It's a number that Isaac Newton came up with that is the basis for all gravitational situations. M1 and M2, that's your mass of your object. That will always be in kilograms. If it's not, you'll need to convert. And then R, your radius or your distance, that's in meters. And again, if it's not, you will need to convert. So how do we measure that gravitational constant? How do we know exactly what that is? So G, capital G, and this is in your reference packet on that first page with all those constants on there. G is actually measured as 6.67 times 10 to the negative 11th. And then that unit that you see there, all that does is make sure that your meters and your kilograms are going to cancel, so that all you are left with is newtons. Okay, so don't worry about the units too much for this one, unless it specifically asks for that. So let's look at an example really quick. You have a large lead ball that has a mass of 5.9 kilograms. You also have a small lead ball that has a mass of 0.047 kilograms, and they're separated by 0.055 meters of space. Find the force of attraction between them. So let's look at our formula. We have G, M1, M2, and R. So I gave you two masses. I gave you 5.9. I gave you 0.047. And I gave you 0.055 meters. So let's plug that all in. You see G there at the very beginning. You see 5.9. You see 0.047. My suggestion would be to you is do everything in the numerator first. Hit enter, get an answer, and then divide by R squared in parentheses. That's going to be the best way for you to solve these problems. Otherwise, there's going to be a lot more parentheses in there so that you can keep everything where it needs to be for this problem. So once you calculate this out, you should get about 6.11 times 10 to the negative 9th newtons, and that should be your final answer. So that's it for today.